Hello, everybody. We've got another career interview and beautiful Olga Ilyachova all the way from Melbourne, where people are protesting, but we're not going to talk about that today. We're going to talk about something else, scientific careers. And not only that, but also academic careers if you are into science, because Olga is somebody who is working for Monash University. Now, Olga, how are you?
I'm good, thank you. How are you?
I'm well, and you know what? I'll just let you to introduce yourself and tell us how you get to where you are right now.
So my name is Olga, as you already gathered, and I work at Monash University. I work as a research fellow and I have almost 10 years of career experience. I did my undergrad back in Moscow. I graduated from Moscow Institute of Physics and Technology with a degree in applied physics and mathematics. And after that, I have applied for a scholarship in Australia to continue my studies and do my PhD. And I originally have chosen physics. So I started my PhD in physics, but I really quickly understood that it's probably not for me. That's not what I was enjoying. And I have transferred to biochemistry. Since then, I've been working pretty much on interface between biochemistry, structural biology, physics, mathematics, and a bit of chemistry. At the moment, I'm located at Monash Institute of Pharmaceutical Science within the Department of Medicinal Chemistry. Saying that, I continue to do structural biology, and I do what I call applied structural biology. That means I work in close collaboration with the medicinal chemists. And to give you a very rough idea of what we do here is we are trying to look for new pharmaceuticals. To look for new pharmaceuticals, you really need to understand the process, how things work, and multiple proteins within this process. So first we identify the target. Target is just a protein either within our body or within a bacteria that we try to alter its function. We either try to stop it working or make it work. And for that, we're actually screening multiple chemicals. And that's where my expertise lies. If you ever seen a picture of a protein, you know, those interesting ribbons, etc., that's exactly what I produce. So I crystallize proteins and after that take them to the synchrotron. I know a lot of complicated words. And after that, I can create this picture of protein bound to a ligand or a chemical. And in that case, we can actually design chemicals to bind the proteins, like a key and like, so they would actually suit to the surface of the protein, and we would have a look at the different properties of the molecules. Without seeing it, it's very difficult to do. And that's what is called structure-based drug design. We know the structure and we are trying to design the drugs.
I feel that
I hope it wasn't too overwhelming.
No, because I think when people listen to this, I will post that on a Sunday. They will be flooding you with questions about, you know what.
Yep.
So you are obviously familiar with how vaccines work. I'm not going to ask you that, though. It's just, you know,
yes.
you obviously have an opinion, but I'm not.
I do have an opinion, but yeah. let's stay away from that.
Yeah, very, very well. So, okay. And now if we have a teenager who is very interested in physics or chemistry, so if you could tell us a little bit about potential pathways through Monash into industries that are on the rise at the moment, where the demand is and what skills you're generally looking for in high school graduates to be successful in this career.
So you always would start with the undergraduate degree. And what I'm trying to say to young people who are trying to understand what they want to do. Do they want to do physics or chemistry or biology or something else? Your undergraduate degree is important, but it's not limiting. So once you do your undergrad degree, you can still change your career, change your views. And if you realize while you're doing it that it's not for you, you probably can always switch the courses. Because realistically, when you're in grade 12 and trying to search for different different units, different degrees, etc., etc., you realistically don't really know what you will be doing at the end. And to be honest, like, that's completely fine, because when I started my degree in applied physics and mathematics, I didn't know as well. But you can always switch. That's the first thing. The other thing is, if you are really inquisitive, if you have really good critical skills, if critical thinking skills, if you want to know how things work, not just the pure facts, like not just number of different things, but you actually want to know why and how, science probably career for you, because there is no standard day for me at work. There is, I don't know what I will be doing in 6 months. Things are changing quite a lot. And what I love the most about my career is that I'm learning a lot. So if I have a look at my job 6 months ago, it wouldn't be the same as now. I would be doing very, very different things. And that's what actually really appreciate by my employer, that I still can learn. And that's what we're expected to do. We're expected to learn all the time. We're expected to deepen our knowledge, to do other things, to do different things. So that's really, really good about science. What else?
Oh, the fields, what fields are
Yeah.
on the rise now? Where is the demand, and where should we be looking into in terms of, maybe niching? If somebody would like to, if somebody is certain they are into chemistry, where is it all going?
So what I have to mention is that at the moment, there are very few people who are working just within one discipline. Most of the disciplines are merged together. Like, if you have a look at my career, I've always been working on the interface of physics and biology and biophysics and biochemistry and medicinal chemistry. And that's where the real demand is, where you understand not just your field, not just chemistry, but actually a few other different things. Well, it's hard to say for all of the industries like mathematics and physics and biology and medicinal chemistry, but within my industry, the skills that are really in demand at the moment, let's say not just biology, but being able to use programming skills as well, because there is a huge amount of data that has been generated in the last 20 years, and not all of it has been analyzed, and we can't really analyze it manually. So if you can still program, that would give you huge advantage. Also, artificial intelligence is a big thing at the moment. So we are changing techniques that we've been using in the last 15, 20 years quite dramatically, because there are new techniques that use artificial intelligence to predict things and enhance our protocols. And it's a steep learning curve, because it's very, very far from what we were actually taught. When I did my PhD, there was no such a thing. And some of the techniques have already died out because we already have artificial intelligence protocols. So that's a big hotspot at the moment. Drug discovery, it's a mix of different skills. It's biology, chemistry, and again, computational skills. That's so it's everywhere now. So to be able to work in our field, you have to have really strong computer-based skills. So you need to know how to deal with the databases, you need to know how to program, you need to know how to script at different levels and analyze data efficiently.
That's very interesting, actually. And then my next question actually comes from this. So how much mathematics is there? Because I'm just relying on the personal experience, because I picked biology as one of my year 12, well, whatever was in Russia back then, subjects, final subjects. And I don't know, I picked it because it was quite interesting. And I did really well in my final exams because I failed maths. However, biology, it was not so much full of numbers as such. There was a lot of language there and analysis. And I'm wondering, So if somebody not so good at maths, could they still be successful in the fields of biology and chemistry?
I think absolutely, if you can apply certain models and formulas to your work, because you would still be doing some computational things. Probably,
right.
To be honest, I don't know. I can't talk about chemistry. I'm not qualified to talk about chemistry. I just work with chemists. I'm not a chemist. So I'm not sure about that part. But in biophysics, in biochemistry, you would still need to be fairly good with the biological concepts. And again, it's going to be your advantage if you are familiar with numbers and how to use the formulas, and you can actually apply that to your graphs, to your experiments, to your hypothesis. It's always beneficial, and statistics as well.
Okay, that's a tough one. Statistics, yep, you got me there. Okay, so in your typical day, as in today, I know you mentioned that 6 months ago you were doing completely different things. And if it's now, what's your day like? So what is it that you're doing in terms of, are you on the computer? Are you analyzing data, or are you in the lab? So what is it like on a typical Monday or Tuesday?
It's a mix of everything. For example, tomorrow I've got a large-scale experiment at the synchrotron, and that means I have to prepare all my crystals for the synchrotron, and that means that the rest of today I will spend in the lab preparing the samples. But after that, the day after tomorrow, I will be analyzing the data. So I will be mostly on the computer, and I will be analyzing the data on the computer, solving the crystal structures. And after that, I will be actually presenting the data to my colleagues. That means I will spend most of the time in the meetings explaining the data, explaining my findings. And if we have a look a little bit in the future, after that, I would obviously need to present the data in a written form. Either it's going to be an article, or I would need to provide our partners with the results. So it can be a report. So yes, I would need to write up my findings in a written form.
So for anyone who is listening, if you are still in years 9 to 12, you be picking up things like you need to be organized, you need to have fairly, decent presentation skills of complex data in some pictorial form, perhaps, so it's easy to understand. I know your academic stuff will probably understand it, but if you were to present it to someone who isn't that tech savvy or science savvy, it has to be easy to digest. You also need to be able to write formal style, academic style, because you will be producing scholarly articles as a result of it. And you need to have all the practical skills to conduct those experiments, right? So quite a few things, all of it really, when you think about it. Okay, so how the academic side of the teaching fits into this now, like in your job? So how many teaching hours do you have, and how do you find that aspect of your job?
So working in academic setting, you can choose to be experimental, like you can choose either to conduct experiments only, so 100% experimental part, so you're not doing teaching, or you can actually switch it to 40-40-20. And even if you are choosing to be lab-based most of the time, you would still have a small component of teaching. It's probably not going to be teaching as lecturing, but you would still have PhD students in the lab and honors students in the lab that you would need to teach how to do things, how the protocols work, how to set up things, etc., etc. So in my case, I mostly at the moment work in the lab. Saying that, we do have honors students, we've got PhD students. I'm not doing lecturing at the moment. I used to do tutorials, but I decided that I enjoy more experimental part of things. So with the PhD students and honor students, they mostly have already some understanding of how things work. And the teaching that we are providing, it would be they pretty much following us and asking questions, and we do explain how things works and what would work, what not would work, and after that we troubleshoot together. Because in the lab lots of experiments don't work. Actually 80% of your experiments wouldn't work, and probably 20 would be just successful. And that's a big thing you have to get used to, just because we work on things that we don't know like the answers to.
So you have to be very patient.
Yes, you have to be very patient, and probably not get upset too quickly, because you have to try multiple times. It's hard to learn things that you don't know anything about, and that's exactly what we do. With the lecturing, you can progress to lecturing, or you can choose to be a lecturer 100% of the time. Actually, at Monash, there are some teaching positions that are teaching positions only. But most of the time you would do mix of things. You would be doing some experimental parts and some teaching. To become a lecturer, PhD most of the time is requirement, unless you are doing lecturing in some of the fields where you can have pre-recognized knowledge or experience, and university would be okay with that. So what I can think of, let's say architects, they don't need a PhD to do lecturing. They most likely would need work experience and go lecture. In our field though, I can't think of a lecturer that doesn't have a PhD and a lot of lab experience. So most of the time lecturers are someone who is holding a lot of grants. They would have their established groups, and they're still publishing, they're still working as scientists, and they would be lecturing 40% of their time.
So how many hours a week do you generally work, like if it's a full-time position?
37.5 at Monash. Well, that's what's said, what it says on the contract, but realistically, the good thing is our jobs are very flexible, because you work around your experiments. But sometimes you can work more, sometimes you can work less. It is flexible, and it goes both ways. Like I've heard that in some industries it doesn't. It means that working flexible, you just work whenever you're required. In our field, it does go both ways, so it can suit you as well.
Right. Okay. I've got a question. I'm not sure whether to ask it or not, but I have
that's all right.
Crying at it, because I cater for Russian-speaking audience. People are coming from Russia, and many of us studied there, and then some of us studied here. Would you be able to give a bit of an insight to parents? Because, a lot of parents, and, in the group, we always compare what it was like for us. And even though the schools is the context, let's just compare the university. And I studied in St. Petersburg, in one of the best universities in Russia, and I've studied here in now 2, and I find that I've been working harder here with the way it's all structured and the requirements and the the criteria. Did you feel the same, or I found studying in Russia was much easier?
It's very different. I can't say the same thing about myself, because I started at Monash Institute. Monash, oh my God, Moscow Institute of Physics and Technology. And our studies were full on. So it's applied physics and mathematics on top of theoretical physics and many other things. But what I found is all the knowledge that I gained from Moscow, I'm not using them at the moment, so they're not applicable in my job. And when I started my PhD in biochemistry, I didn't even know how to use a pipette, because although I graduated from the Department of Molecular and Biological Physics, and I had lots and lots of theoretical knowledge, I didn't have practical knowledge. Saying that, I'm not saying it was all bad, because I do have this advantage of understanding it on deeper level, but it didn't prepare me for a PhD, at least in biochemistry whatsoever. Here, when honor students come to the lab, they have they have a lot of experience with what they're supposed to do. So they're almost ready. You still need to supervise them, obviously. It's still part of their degree, and it's very different to do, like, a lab in undergrad course and to conduct your own experiments. But saying that, they're very prepared. They're prepared to use the methods that we want them to use. They know how things work, and they're ready. So they're job ready. It is intense, especially I haven't started PhD in Moscow. I just did PhD here, so it would be. I suspect it would be different, but it's very intense. It's hard to get a degree. It's probably not that hard to go through the 4 years. The hardest part would be to finish your thesis, to write everything up, to present your data. So it's a steep learning curve. And at the beginning, I was surprised, because when I started to do demonstrating in the year 1 labs, just to fresh university students, I couldn't understand why they're coming in from school and they're learning Ohm's law and those things that we're learning like at grade 6 or 7 or whatever. I don't remember what grade it was, to be honest, but still it was very, very basic. But from there, from these basics, they progressed really, really quickly to quite good level. So by the 4th year studying in university, they are specialists. They can go into the lab. They can grasp like really difficult concepts, and they're very, very successful in what they're doing. And after that, they're prepared to do their PhDs. They're prepared to do their honors. And ultimately, if you have a look at Monash Institute of Pharmaceutical Science, at the moment, I think we are ranked number 2 or 3 in the world in pharmacy and pharmacology. And our graduates are highly demanded. Like if they want to go somewhere, they will find jobs around the world, and in Australia as well. So I think it's just different. It's not easier. It's not more complicated. I think it's very, very different, and students are more prepared than we were.
I think this is actually, you put it nicely when you said job ready, because when I put it in easier, what I meant, I guess, is we were presented with a lot of knowledge, but we were unprepared to apply it. Whilst here, I found the studies are so much harder because there's so much application straight away. And I feel that I'm more equipped to go into workforce, and I don't have to go blind and, as you've said, job ready. And I guess it comes with hard work.
It does. You need to you need to have certain skills. Like if we look at the academia, you need to be able to write, and we definitely were not prepared for that. And students here in Australia are writing reports and papers. For example, now our department has switched for honors students, they're not anymore writing their honors thesis, they're actually writing academic paper. So at the end of their honors year, they're producing a paper, and that's really, really that's really valuable for them, because at the end of the day, that's one of our metrics. We are meant to be able to write academic text. We are meant to be able to write publications, and it's really difficult coming from I come originally from Belarus, but I studied in Russia.
Yeah, me too.
Oh, right. Okay.
Yay.
It's always, do remember, with all the compositions that we were writing, they were always meant to be saying certain things in certain ways, and our minds were shaped in certain ways. And here students are actually taught to express themselves really well within the boundaries and within the styles, and that's great. They're taught how to prepare posters, presentations, publications, to write grants in some cases, like it's not for PhD students, but anyway, so to write proposals. we didn't have that.
Yeah, I'm a big advocate of this. I always say, you know what, they can write here and they can write pretty much anything. And from the early age, primary school, they're taught all sorts of text types. And as you mentioned, I'm studying now, and you're right, at the higher postgrad levels, they're expecting us to produce scholarly paper that could be published. So I couldn't even thought of that when I was studying back
And
in
they're
Russia.
not afraid of writing. And
Not
what I
a- yeah,
found
true.
with many people who come here to do PhD, we are afraid of writing. We are afraid of writing something wrong. And it's very difficult to switch your mind from that. So
Oh, this
yeah,
is like, this is so close to home, because I work with students coming from Russia, and they just literally ask me, tell me, what do I need to write?
Yeah.
And it's so, it's just something that Australian students would never ask, right? Because they're taught to express their thoughts within the constraints of the text type and, like, you know, based on referencing and all. Yeah, you brought up a very valuable point. That was good. Thank you.
Yeah, another thing, they're not afraid of making mistakes and asks, like they're not afraid to ask questions, which is really, really good. I found that students from other countries, they would rather do something wrong in the lab instead of looking. It's not just Russian students.
There's a cultural thing, and I guess it has to do with the
They would much
parenting
rather
style.
go and try and do their thing and do it wrong than ask a question, like a simple question. And it's really, really difficult to work with the students that don't want to ask questions, because I can't really teach them much.
Right. Oh, that's very interesting. I think it's going to be very valuable for the parents, because, you know, coming from a culture where you give the answer and you know you're wrong. Yes, you're right. And here, like, I'm watching my kids coming home, and they always go, no, errors are just another learning curve. It's okay. We actually have to make them. So different mindset completely. Okay, well, look, it was great. I feel today we've covered science and academic side of it. So for young people who are interested in a practical application of science, they know there is work, right? And for people who love that, plus passing their knowledge in the academic field, there is an avenue for that. And I guess everybody understands that you have to have an array of skills to be successful in this career. You have to speak, you have to write, you have to be organized, you have to be curious, and most importantly, you have to be very patient, because 80% of the experiments, they just fail.